The year was 1942. The sky above southern England buzzed with the constant hum of aircraft engines. Hurricane fighters roared overhead on patrol while Spitfires dove and climbed in training formations. But deep inside a cluttered workshop at the Royal Aircraft Establishment, a young engineer named Frank Whittle sat hunched over blueprints that no one else believed in. His hands were stained with grease and ink. His eyes burned from squinting at calculations by lamplight. Around him, senior engineers shook their heads and muttered about wasted resources. They called his design impossible. They said it violated basic principles of flight. Some laughed outright. But Frank kept working because he could see what they couldn't. He understood that the war would be won not by following old rules but by breaking them. And in his mind he had already solved the problem that was killing Allied pilots faster than enemy bullets. The problem wasn't courage. British pilots had plenty of that. The problem wasn't training or tactics. The Royal Air Force had the best of both. The issue was speed. German Messerschmitt fighters were simply faster than anything the Allies could put in the air. They could choose when to fight and when to flee. They could outrun pursuit and overtake bombers with ease. Every dogfight became a chess match where the enemy moved twice for every Allied move. And Frank Whittle, working alone in a workshop that smelled of oil and desperation, was about to change everything. Who was Frank Whittle? Before the war, before the engines, before his name became synonymous with revolution, Frank Whittle was just a curious boy from Coventry with dirt under his fingernails and stars in his eyes. He was born in 1907 to a family that knew the value of hard work but little else. His father operated a small machine shop, the kind of place where broken things came to be fixed and impossible things came to be built. Frank spent his childhood there, watching sparks fly from grinding wheels, listening to the precise rhythm of lathes, learning that every problem had a solution if you were willing to think hard enough. By age 12, he was taking apart clocks to understand how gears meshed. By 15, he had built a working steam engine from scrap metal and determination. His teachers noticed something unusual about the boy. He didn't just memorize formulas, he questioned them. He didn't just solve problems, he found new ways to solve them. When other students calculated the speed of falling objects, Frank wondered why objects had to fall at all. When they studied the lift generated by airplane wings, he imagined wings that didn't need to flap through air but could push the air itself. In 1923, at 16, Frank enlisted as an aircraft apprentice with the Royal Air Force. Not because he wanted to be a pilot, though he would eventually earn his wings, but because he wanted to understand flight from the inside out. He studied every bolt, every wire, every control surface. He learned how engines turned fuel into power, how propellers turned power into thrust, how wings turned thrust into flight. But more importantly, he began to see the limitations in everything he studied. The inefficiencies, the compromises, the places where physics was being instead of harnessed. During his service, Frank watched other engineers make incremental improvements. They added horsepower to engines, refined the pitch of propellers, adjusted the camber of wings. Each change brought small gains. A few miles per hour here, a bit more climb rate there. but Frank saw the bigger picture. He understood that they were all working within the same fundamental framework, a framework that had reached its limits. Propeller-driven aircraft could only go so fast before the propeller tips approached the speed of sound and efficiency collapsed. Piston engines could only burn fuel so efficiently before heat and friction consumed the gains. The entire system was approaching a wall that incremental improvements couldn't breach. So Frank began sketching something different. Not better propellers or more powerful pistons, but an entirely new way to think about propulsion. Instead of spinning blades to grab air and pull an aircraft forward, why not suck air in, compress it, ignite fuel inside it, and blast the expanding gases out the back? The concept was elegant in its simplicity. Air goes in one end, fire and pressure cook it in the middle. Thrust comes out the other end. No spinning propeller to limit speed. No complex transmission to waste power. Just pure reaction, like a rocket but breathing air instead of carrying its own oxygen. The idea consumed him. During off-duty hours, he filled notebooks with calculations. He sketched turbine blades and combustion chambers. He worked out compression ratios and fuel flow rates. He even built small working models that sputtered to life on his workbench, producing tiny jets of flame and noise that proved the concept worked, at least in miniature. But when he showed his designs to senior officers, they dismissed them as fantasy. When he submitted formal proposals, they were filed away and forgotten. The Air Ministry had more pressing concerns than the wild theories of a junior engineer. Frank persisted anyway. He refined his calculations, improved his designs, built more sophisticated prototypes. He studied the work of other inventors who had dabbled in jet propulsion, learning from their failures as much as their successes. He corresponded with university professors who understood the theoretical foundations of his work, even if they doubted its practical applications. And slowly, methodically, he transformed his impossible dream into detailed engineering specifications. By 1930, Frank had completed his first comprehensive design for what he called a turbojet engine. The patent application he filed that year described a machine that seemed to belong in science fiction rather than an aircraft hangar. It used a centrifugal compressor to squeeze incoming air, a combustion chamber to ignite fuel in the compressed air, and a turbine to extract energy from the expanding gases while directing the remainder out as thrust. On paper, it promised to deliver more power per pound than any piston engine while operating at altitudes where propellers became useless. The patent was granted, but that was where official interest ended. The Air Ministry reviewed Frank's proposal and concluded that while the science was sound, the engineering was impossible. The materials needed to withstand the heat and stress didn't exist. The precision manufacturing required was beyond current capabilities. The fuel consumption would be enormous. And even if all those problems could be solved, they estimated it would take at least 20 years to develop a practical engine. Frank disagreed with their timeline, but he couldn't argue with their technical actions. These was real problem materials. The manufacturing challenges were genuine. The fuel efficiency concerns were valid. So he went back to work, not to abandon his design, but to solve the problems that made it impossible. He studied metallurgy, learning about alloys that could withstand extreme temperatures. He visited factories, understanding how precision parts could be manufactured at scale. He calculated fuel consumption curves, finding ways to improve efficiency without compromising performance. For over a decade, Frank worked in relative obscurity. He taught other engineers, published technical papers, and continued refining his jet engine design. Most of his colleagues forgot about his unusual obsession. Some assumed he had moved on to more practical projects. But Frank never stopped believing that his engine would fly, that it would transform aviation, that it would arrive just in time to change the course of the war that everyone could see coming. And then in 1939, everything changed. Germany invaded Poland. Britain declared war. Suddenly, the impossible became essential, and the impractical became urgent. Frank Whittle's ridiculous engine was about to get its chance to prove sometimes that the most revolutionary ideas come from the most unexpected places. The war changed everything overnight. In September 1939, as German tanks rolled across Poland and Britain braced for invasion, the Air Ministry suddenly found itself interested in ideas they had dismissed for nearly a decade. Frank Whittle's jet engine proposal was pulled from dusty filing cabinets and placed on the desks of men who now understood that conventional thinking might not be enough to win this war. They still called it experimental. They still questioned whether it could work. But for the first time they were willing to find out. Frank was given a small team, a modest budget, and a converted garage in Rugby. It wasn't much, but it was more than he had ever hoped for. His workshop smelled of metal shavings and burnt oil. The concrete floor was stained with grease and marked by the tracks of heavy equipment. Workbenches lined the walls, cluttered with precision instruments, half-assembled components, and notebooks filled with calculations that most engineers couldn't understand. In the center of it all sat Frank's first full-scale prototype, a machine that looked nothing like any aircraft engine anyone had ever seen. Where conventional engines had pistons and cylinders, Frank's design had a spinning compressor wheel. Where others had carburetors and spark plugs, his had fuel injectors and continuous combustion. Where traditional engines turned crankshafts to drive propellers, his created pure thrust by accelerating hot gases through a carefully shaped nozzle. It was alien technology built with familiar tools, revolutionary thinking expressed in steel and aluminum. The first test runs were disasters. The compressor wheel shattered at high speed, sending metal fragments ricocheting around the test chamber like bullets. The combustion chamber overheated in war that allowed gap sped, creating flames to escape where they shouldn't. Fuel pumps failed, bearings seized, and control systems malfunctioned. Each failure taught Frank something new about the challenges he faced, but they also reinforced the skepticism of those who had doubted him from the beginning. His critics weren't entirely wrong. The materials available in 1940 were barely adequate for the stresses his engine created. Steel that worked perfectly in piston engines melted or cracked under the extreme temperatures of jet combustion. Bearings that had operated reliably for decades in conventional applications failed within hours when exposed to the vibrations and heat of his turbine. Even basic components like fuel lines and gaskets required complete redesign to function in an environment where temperatures could exceed 1,000 degrees and pressures could crush conventional parts like paper. But Frank was relentless. Every failure was followed by analysis, redesign, and another test. He collaborated with metallurgists to develop new alloys. He worked with bearing manufacturers to create components that could survive in his engine's harsh environment. He refined his combustion chamber design dozens of times, adjusting fuel injection patterns, airflow paths, and cooling strategies until the flames burned where they were supposed to and nowhere else. The breakthrough came in April 1941. After months of failures, 18 modifications, and incremental improvements, Frank's engine finally ran for more than a few minutes without destroying itself. The sound was unlike anything anyone had heard before. A high-pitched whine that rose and fell with engine speed, punctuated by the deep roar of exhaust gases accelerating through the nozzle. It was the sound of the future arriving ahead of schedule. The performance numbers were astounding. Frank's engine produced more thrust per pound than the most powerful piston engines while weighing significantly less. It operated efficiently at altitudes where conventional engines gasped for air. And most importantly, it promised to push aircraft to speeds that would make current fighters obsolete overnight. The theoretical top speed of a jet-powered fighter was limited not by engine performance but by the structural integrity of the airframe itself. Word of the successful tests reached the highest levels of government within days. Winston Churchill himself was briefed on the project and immediately grasped its significance. This wasn't just a new engine. It was a potential war winner, a technology that could restore British air superiority and turn the tide of aerial combat. Churchill ordered full government support demand for the project and flying that within months prototype be ready, not years. The pressure was immense. Frank's small team was expanded rapidly, drawing engineers from across Britain's aircraft industry. The converted garage was abandoned for a proper facility with testing equipment, machine shops, and assembly areas. Government owed to suppliers contracts who could provide the specialized materials and components needed for production. What had been one man's obsession became a national priority almost overnight. But turning a successful ground test into a flying aircraft presented entirely new challenges. The engine had to be integrated into an airframe designed for jet-specifically propulsion. Traditional aircraft designs assumed the engine would be mounted in front, the pulling aircraft through the air with a propeller. Frank's engine pushed from behind, requiring completely different weight distribution, air intake systems, and control arrangements. The aircraft that would carry his engine had to be as revolutionary as the power plant itself. The Gloster Aircraft Company was chosen to build the airframe, and their chief designer, George Carter, worked closely with Frank to create something that had never existed before. They called it the Gloster E.28/39, and it looked more like a metal bullet with wings than a conventional fighter. The fuselage was sleek and narrow, optimized for high-speed flight rather than the rugged utility of existing designs. The wings were thin and straight, built for efficiency rather than the forgiving handling characteristics that pilots were accustomed to. Every line of the aircraft spoke of speed, of a machine designed to cut through air rather than wrestle with it. The first flight was scheduled for May 1941, just 1 year after Frank's engine had achieved its first successful ground run. Test pilot Jerry Sayer climbed into the cockpit knowing he was about to experience something no human being had ever felt before. There was no propeller spinning in front of him, no familiar vibration of pistons firing in sequence. Just the smooth whine of the turbine and the knowledge that he was sitting atop a controlled explosion that would either lift him into history or incinerate him in a ball of experimental failure. At precisely 10:30 in the morning, Sayer advanced the throttle and felt the aircraft surge forward with an acceleration unlike anything he had experienced. The takeoff roll was shorter than expected. The climb rate was phenomenal. And once airborne, the little aircraft flew with a smoothness that made conventional fighters feel crude and mechanical by comparison. There was no propeller wash buffeting the control surfaces, no torque trying to roll the aircraft, no complex engine management required. Just pure, clean speed that seemed to increase effortlessly with each touch of the throttle. The flight lasted only 17 minutes. But those 17 minutes changed aviation forever. When Sayer landed and climbed out of the cockpit, he was grinning like a man who had seen the future and found it exhilarating. The aircraft had performed flawlessly. The engine had operated smoothly throughout the flight, and the speed achieved had exceeded every prediction. Frank Whittle's impossible dream had just become Britain's secret weapon, though the war would test whether that weapon could be deployed before it was too late. The test flights multiplied rapidly. Within weeks, Sayer was pushing the Gloster E.28/39 to speeds that made conventional fighters look like they were standing still. On one memorable afternoon in June, he achieved 370 miles per hour in level flight, a velocity that would have required a Spitfire to dive steeply just to match. But speed was only part of the revolution. The jet climbed to altitudes where piston engines wheezed and struggled, where the air was so thin that propeller-driven aircraft could barely maintain level flight. At 30,000 feet, Frank's engine was just hitting its stride. The implications were staggering. German bombers that relied on high altitude to avoid interception would find nowhere to hide. Enemy fighters that depended on speed and climb rate for tactical advantage would be outmatched in every category. The balance of air power, so carefully calculated by both sides, was about to shift dramatically. But Frank understood something that excited politicians and terrified engineers. His prototype was just the beginning. The engine that powered those early test flights was primitive compared to what was possible. Even as the E-28/39 proved the concept, Frank's team was already working on the next generation. They called it the W2, and it promised to double the thrust of the original design while improving fuel efficiency and reliability. The new engine incorporated lessons learned from hundreds of hours of testing. The compressor wheel was redesigned for better airflow and higher pressure ratios. The combustion chamber was reconfigured to burn fuel more completely while running cooler. The turbine blades were crafted from new alloys that could withstand temperatures that would melt conventional steel. Manufacturing became the critical challenge. Building one experimental engine in a garage was difficult enough. Building hundreds of production engines required industrial capabilities that simply didn't exist. New factories had to be constructed. Specialized tooling had to be designed and manufactured. Workers had to be trained to handle materials and processes they had never encountered before. The precision required was extraordinary. Turbine blades had to be balanced to tolerances measured in thousandths of an inch. Combustion chambers had to be welded with techniques that prevented warping under extreme heat cycles. Frank found himself traveling constantly between design offices, factories, and government ministries. His role had evolved from inventor to project manager, from dreamer to deadline-driven executive responsible for delivering a miracle on schedule. The pressure was relentless. Intelligence reports indicated that German engineers were working on similar projects, racing against an enemy's research program while simultaneously perfecting revolutionary technology created stresses that kept Frank awake most nights, poring over production schedules and performance specifications by lamplight. The breakthrough in manufacturing came from an unexpected source. Rolls-Royce, the company famous for luxury automobiles and reliable aircraft engines, initially dismissed jet propulsion as an interesting curiosity. Their engineers were committed to perfecting piston engines, squeezing every possible horsepower from conventional designs. But when government officials showed them classified performance data from Frank's tests, their attitude changed overnight. Suddenly, Britain's most prestigious engine manufacturer was asking how quickly they could begin production of this revolutionary power plant. Rolls-Royce brought industrial expertise that Frank's small team couldn't match. They understood how to scale production from prototypes to mass manufacturing. They had relationships with suppliers who could provide specialized materials. Most importantly, they had quality control systems that could ensure every engine met the exacting standards required for military service. The partnership transformed Frank's invention from experimental technology into practical weapons of war. The first production engines rolled off Rolls-Royce assembly lines in early 1943. They were designated the Welland, and they produced over 1,500 pounds of thrust while weighing less than 800 pounds. By comparison, the most powerful piston engines of the era weighed over 2,000 pounds. And produced equivalent thrust only when turning massive propellers that created their own problems at high speeds. The weight savings alone revolutionized aircraft design, allowing engineers to build faster, more maneuverable fighters that could carry heavier armament and more fuel. But Frank's engines were still considered too experimental for frontline combat. The Air Ministry wanted more testing, more reliability improvements, more assurance that these revolutionary machines wouldn't fail when pilots depended on them most. Fighter pilots were understandably nervous about flying behind engines that had no historical track record. Piston engines had decades of operational experience. Jet engines had months. The psychology of trust had to be built alongside the technology itself. The solution came through gradual introduction. Selected squadrons received jet-powered aircraft for training and evaluation, allowing pilots to experience the new technology without the pressure of combat missions. Their feedback was invaluable. They reported that jet engines were actually more reliable than piston engines in many respects. No complex ignition systems to fail, no cooling systems to leak, no propeller reduction gears to strip. Just a continuous burning process that either worked or didn't, with very little middle ground. Pilots also discovered tactical advantages that engineers hadn't anticipated. The smooth power delivery of jet engines made precision formation flying easier. The absence of propeller wash improved gunnery accuracy. The high-altitude performance opened entirely new combat strategies. Most surprisingly, the psychological effect on enemy pilots was significant. German fighters that had grown accustomed to outrunning British aircraft suddenly found themselves being overtaken by mysterious aircraft that made unfamiliar sounds and climbed at impossible angles. By late 1943, intelligence reports confirmed Frank's worst fears. German engineers had indeed developed their own jet engines, and their first jet fighter, the Messerschmitt Me 262, was already in limited production. The technological race that had begun in British workshops was now a full sprint between industrial powers, with air superiority hanging in the balance. Frank's early lead was shrinking, and the window for decisive advantage was closing rapidly. The pressure to deploy British jet fighters operationally became overwhelming. Politicians demanded immediate action. Military commanders insisted that the technology was mature enough for combat use, but Frank remained cautious, understanding that premature deployment could result in catastrophic failures that would set the entire program back months or years. His reputation as an innovator was now balanced against his responsibility as an engineer who knew the difference between laboratory success and battlefield reliability. The compromise was elegant in its simplicity. A small number of jet fighters would be deployed in carefully controlled circumstances with experienced pilots and extensive ground support. Any problems would be addressed immediately, and lessons learned would be incorporated into the next production batch. It was controlled operational testing disguised as combat deployment, allowing the technology to prove itself under real conditions while minimizing the risks of spectacular failure. The first operational squadron to receive jet fighters was number 616, based at Culmhead in Somerset. The pilots were hand-picked veterans, men who had survived the Battle of Britain and understood both the capabilities and limitations of conventional aircraft. When they first saw the Gloster Meteor F1, powered by Frank's Welland engines, their reactions ranged from fascination to skepticism. The aircraft looked alien compared to their familiar Spitfires and Hurricanes. No propeller dominated the nose. Instead, sleek air intakes flanked the cockpit like gaping mouths hungry for atmosphere. Squadron leader Andrew McDowell was among the first to fly the Meteor operationally. His initial impression was disbelief at the acceleration. Where conventional fighters built speed gradually, the jet surged forward with an immediacy that pressed him into his seat. The climb rate was extraordinary, reaching altitudes that would have taken a Spitfire twice as long to achieve. But it was the silence that struck him most. Without a propeller chopping through air directly ahead, the cockpit was eerily quiet except for the distant whine of the turbines behind him. The early operational flights revealed both the promise and the problems of jet technology. Pilots reported that the engines were remarkably smooth, free from the vibration and torque effects that characterized piston engines. Fuel consumption was higher than expected, but the performance gains more than compensated. At altitude, the Meteors could outrun anything the Luftwaffe possessed. They climbed faster, flew higher, and maintained their performance in thin air where conventional fighters struggled. But there were complications. The engines took longer to respond to throttle inputs than piston engines, requiring pilots to anticipate power changes well in advance. The aircraft's handling characteristics were different enough that experienced pilots had to relearn fundamental techniques. Landing speeds were higher, approach angles steeper, and the absence of propeller wash meant that control surfaces behaved differently at low speeds. Every flight was a learning experience, every mission an experiment in applied physics. Frank spent most of his time during this period visiting operational squadrons, talking to pilots, observing maintenance procedures, and identifying improvements for the next generation of engines. He carried notebooks everywhere filled with sketches and calculations based on real-world feedback. A pilot's complaint about throttle response became a redesign of the fuel control system. A mechanic's observation about turbine blade wear led to metallurgical improvements that extended engine life by hundreds of hours. The intelligence war was as intense as the technological race. British agents reported that German Me-262s were experiencing significant problems with engine reliability and pilot training. Their Jumo 004 engines had a service life measured in dozens of hours rather than hundreds, forcing frequent replacements that strained German manufacturing capacity. More critically, Germany's fuel shortages meant that jet pilot training was severely limited. Their revolutionary aircraft were flying with inexperienced crews who couldn't fully exploit the technology's advantages. Frank's engines, by contrast, were approaching the reliability of conventional power plants while delivering performance that conventional technology couldn't match. The Welland engines in the early Meteors were running for hundreds of hours between overhauls. Maintenance procedures had been simplified to the point where squadron mechanics could service them with minimal specialized training. Most importantly, British fuel supplies remained adequate for extensive pilot training programs that were producing jet-qualified aircrew faster than aircraft could be manufactured. The first combat encounter between jet fighters occurred on July 27, 1944, when Flying Officer Dean of No. 616 Squadron intercepted a German V-1 flying bomb over Kent. The pilotless missile was traveling at nearly 400 miles per hour, fast enough to outrun most conventional fighters. But Dean's Meteor caught the V-1 easily, matching its speed before closing to firing range. His cannon burst shattered the missile's wing, sending it tumbling into an empty field where it exploded harmlessly. The engagement lasted less than 2 minutes, but it marked the beginning of jet combat operations that would define the future of aerial warfare. Word of the successful interception spread quickly through both military and political circles. Churchill was briefed within hours and immediately demanded expanded deployment of jet fighters. The Air Ministry, previously cautious about operational use, suddenly found itself under pressure to accelerate production and training programs. Frank's impossible engine had just saved British lives in actual combat, transforming skeptical observers into enthusiastic advocates overnight. The tactical implications became clear within weeks. V-1 flying bombs, previously capable of penetrating British defenses through sheer speed, were now vulnerable to interception throughout their flight path. German reconnaissance aircraft that had relied on altitude and velocity for survival found themselves being overtaken by British jets climbing at angles that seemed to violate physics. Most significantly, the psychological impact on German aircrew was substantial. Luftwaffe pilots who had grown accustomed to technological superiority suddenly found themselves flying obsolete aircraft against enemies who possessed capabilities they couldn't match or even understand. Frank watched these developments with mixed emotions. Pride in his achievement was tempered by understanding of what it meant. His engines weren't just powering faster aircraft, they were changing the fundamental nature of aerial combat, making existing fighters as obsolete as cavalry against machine guns. The war that had driven his innovation was demonstrating the terrible efficiency of revolutionary technology applied to destruction. Production demands escalated beyond anything Frank had imagined. Rolls-Royce was manufacturing engines as quickly as materials and skilled labor allowed, but demand exceeded capacity by enormous margins. The Air Ministry wanted hundreds of jet fighters within months. Allied nations were requesting access to the technology for their own air forces. Even the Soviet Union, despite political tensions, was expressing interest in jet propulsion through diplomatic channels. The solution required expanding manufacturing beyond a single company. De Havilland was brought into the program to produce an improved engine designated the Goblin, incorporating refinements that Frank's team had developed through operational experience. Rover, previously known for luxury automobiles, was tasked with manufacturing components for both Rolls-Royce and de Havilland engines. The entire British engineering establishment was being reorganized around technologies that hadn't existed 5 years earlier. Frank found himself consulting on projects he had never imagined. The Royal Navy wanted jet engines for carrier-based aircraft, requiring modifications for saltwater environments and catapult launches. Bomber Command was interested in jet-powered heavy aircraft that could outrun interceptors while carrying massive bomb loads. Transport Command in liners that could carry Vision jet air passengers at speeds approaching those of military fighters. His simple idea for improving fighter performance was spawning entire industries. But the most significant development was occurring in secret facilities where Frank's engines were being studied not just for improvement but for revolution. Engineers were experimenting with swept wings that could delay the onset of compressibility effects at high speeds. Aerodynamicists were exploring supersonic flight regimes that would require entirely new approaches to aircraft design. Materials scientists were developing alloys and composites that could withstand forces and temperatures beyond anything previously encountered. The war was accelerating technological progress at unprecedented rates. Ideas that might have taken decades to develop in peacetime were being tested and implemented within months. Frank's jet engine was both catalyst and beneficiary of this acceleration. Each operational flight provided data that informed the next design iteration. Every combat engagement revealed capabilities that suggested new applications. The feedback loop between innovation and implementation was compressed from years into weeks. By early 1945, British jet fighters were achieving performance levels that made the original Gloster E.28/39 seem primitive. The latest Meteors were approaching 500 miles per hour in level flight while climbing to altitudes above 40,000 feet. More importantly, they were doing so reliably, with engine failure rates lower than many conventional aircraft. Frank's impossible dream had become routine military equipment, so successful that pilots were beginning to take its revolutionary capabilities for granted. The transformation wasn't limited to Britain. Intelligence reports indicated that American engineers were developing their own jet engines based on technology-sharing agreements. The Soviet Union had captured German jet research facilities and was attempting to reverse engineer their own propulsion systems. Sweden, Switzerland, and other neutral nations were quietly investigating jet technology for post-war applications. Frank's innovation had triggered a global race toward technological capabilities that would reshape not just military aviation, but civilian transportation, industrial processes, and scientific research. Frank Whittle never set out to change the world. He just wanted to solve a problem that was getting pilots killed. In a cluttered workshop that smelled of oil and determination, armed with nothing but curiosity and stubbornness, he took an idea that everyone called impossible and made it fly. His jet engine didn't just boost fighters by 120 miles per hour. It shattered the ceiling of what aviation could achieve, transforming aircraft from mechanical contraptions into pure expressions of speed and power. The boy from Coventry who took apart clocks to understand time had given humanity a way to compress distance itself. His ridiculous propeller that wasn't a propeller at all became the foundation for everything that followed. Supersonic flight, commercial aviation, space exploration, all of it traces back to Frank's simple insight that sometimes the best way forward isn't to improve what exists, but to imagine what doesn't. Today, every time you hear the whine of a jet engine overhead, you're witnessing the echo of one man's refusal to accept limitations. Frank Whittle proved that the most revolutionary ideas often come from the most unexpected places. From people willing to work in silence while others laugh. From minds that see solutions where others see only problems. Sometimes changing the world starts with changing the way you think about what's possible.